All right, so chapter 14, we're talking about graph theory. So we're going to start with 14.1, which is really just a lot of definitions and terms that we have to get familiar with in this chapter so we can understand the later sections. Okay, so here's an example of a graph. We're going to go through what each of these lines mean and what this little thing means. So let's start off with the basic definition of a graph. So a graph consists of a finite set of vertices and edges that start and end at vertices. Okay, they're kind of like line segments. This counts as an edge, even though it's not really it's not a line segment. But if something starts and ends at a vertice, that makes up this graph. So now we're going to talk about some of these words I just mentioned, like vertices and edges. A vertex is a point or a dot of a graph. And of course, earlier I said vertices, so the plural of vertex is vertices. So this is an example of a vertex. I'm going to label this graph, just labeling what some of these things are. An edge is the line or curve, so technically that's an edge of a graph. So this is an edge. Let me write it this way. This is an edge, and actually this thing, it also has another name, this right here, and we'll get to it. But those are examples of edges, and technically this is an edge too, so an edge. These are all edges. There are more edges. All right. These, by the way, these definitions are on Moodle. You can download the notes. If you do want to try to copy these down, because for me, when I take notes in a class, I like to copy what the teacher is writing. And I went ahead and wrote these all out just to save time in the video. I'm going to try to make this one video with all the terms and definitions. But at any time, if you're trying to copy it, just pause the video and you can write them down verbatim as I have here. A path is a connected sequence of edges that start at one vertex and ends at another vertex. Path cannot repeat edges. So for example, I can't go back if I'm looking at like AE. I can't go back on AE ever. So a path could be like AEB, back to A, but I couldn't go AEBEA. I can't go back on myself. Okay. A circuit is a path that starts and ends at the same vertex. So a circuit, actually I kind of confused the two there. A circuit would be ABEA. A path could just be ABCD and it could stop at D, or ABC or ABE. But if I come back to myself, to my original starting spot, that's a circuit, EDCB. Okay, those are circuits. And then a loop is that weird looking thing down here where F is. This is a loop as well as an edge, but because it kind of comes back on itself, that is a loop. A loop is an edge that starts and ends at the same vertex. Okay, so I guess an example of that would be something like this. I'll call it J. So this loop maybe goes out this way and it comes back that way. But that's an example of a loop. All right, next. So I want to keep referring back to my graph that I drew earlier, because we're going to we labeled some of these things, but we want to talk more in depth. So this graph has 6 vertices, And they are the letters I labeled, A, B, C, D, E, F. Now underline that. And we're gonna do this one together. The graph has 8 edges, and they are, oh, I already did it. The graph has 8 edges, and what I mean by an edge is AB, BC, CD, DE, EF. This F is also an edge, and I'll show you how we will label that. So they are AB, BC, CD, DE, BE, and FF. So if I have a loop, call this my loop here. That's how we're going to label a loop, as the letter twice, because it starts and comes back to itself. So this is something I wanted to mention about edges. First of all, I could write an edge AB, that edge AB as BA, and it's the same thing. So as long as I write the 2 vertices that connect together, that is an edge. So AB is BA. And we don't put commas between the vertices. So if I want to say the vertex, for edges, we don't put commas. So I wouldn't say A comma B. If I'm talking about an edge, I only use the commas to kind of space out all of my vertices. And so an edge could be a curve, a line, or a loop. What I mean by a curve is, for example, C to D, I could have done some weird like semicircle or weird loop, kind of shape. It doesn't have to be a straight line like a polygon. And you'll see examples in the homework. So the first question I have is to find a path from B to D. All right. So from B to D, here's B, and I want to get to D. Okay. B, well, to get to D, I could go B, C, D. B, C, D. That's one option. I could go, what else could I do? I think we're going to put parentheses here for the homework. B to C to D. I'll write that here. B to C to D. That's one way. I could go B, E, D, right? I could go B, E, D. But I could be more creative than that. That's like the quickest route to D. I could go B, see if you can see it all, A, E, B, A, E, D. That works. But if I went to F from E, I would end up having to come back on myself. So that's, I think, all of them. And now I want to find a circuit beginning with A. Okay. So I guess I'll think, because I really want to see what I'm writing, and I want to see this. I'm going to write this up here. Number 2 was a circuit beginning with A. So I'm going to go back up here so I can see this graph. So beginning with A, I have to come back to A, by the way. So A, B, E, A. We mentioned that earlier. So A, B, E, A, B, E, A. I could go the other way. A, E, B, A. Now, you may think that's the same thing because it's kind of the same triangle, but these are 2 different circuits. So just make a note of that. 2 different circuits. There's more. I could go A, B, C, D, E, A. A, B, C, D, E, I could go the other way, A, E, D, C, B. A, E, D, C, B, A. Okay. All right, so that is circuits. Now, on my next page, so I gave you some definitions. We went up to number 6 on the previous page. We're going to have about 13 totals. So I needed to kind of take a break to talk about some of these terms before we got too deep into it. So here's my graph again. Number 7 is the degree of a vertex. What that means is it's the number of edges that meet at that vertex. So A, for instance, there are 2 edges. Boom, boom. So the degree of A is 2. The degree of B, notice there are 3. Boom, boom, boom. So the degree of B is 3. The degree of E is 1, 2, 3, 4. Now what happens at F? That's weird. All right, we'll get to that, don't worry. All right, an odd vertex is a vertex whose degree is odd. Okay. Remember here, B, the degree of B was 1, 2, 3, so B is odd. Whereas A is even, 1, 2, and E is even, 1, 2, 3, 4. So that's how we determine even versus odd. So then that brings us up to even. Well, vertex is even if its degree is even. But then it needs to be said that a single loop has a degree of 2. So I did it here. So here at F, that's what we're going to look at in a second. But to do an example, we'll call this J again. This loop J is a loop by itself, and it has a degree of 2. Okay, that's what we're going to call that now. So find the degree of each vertex and state as if it's even or odd. And I've listed them out, so we don't have to do that again. All right, so let's see. I think I've got several pictures of my graph, so I can just use that. So we can see everything together. There we go. All right, so for part A, or I'm sorry, for the degree of A, there are 2 edges, so the degree of A is 2. So is 2 an even or an odd number? It is an even number, so put even right there. The degree of B, 1, 2, 3. 3 is an odd number. The degree of C, 1, 2. 2 is an even number. The degree of D, 1, 2. That is an even number. Degree of E, 1, 2, 4. Even. And then we get to F. This is a little weird. The degree of F is 1. And then we said a single loop was 2. So 1, 2, 3. That's odd. Okay, so a single loop is 2. But if I connect to it as well with something else, that makes it change. Okay, so that's how that works. All right. And we got some more definitions. We'll go through those. So a graph is connected if there's a path between any pair of vertices. All right. So if I have any 2 vertices, can I get there? Can I get to something through, other vertices? So this guy is connected because if I want to get from A to F, I can take a path to do that, or F to anything. So this guy is connected. All right, that makes sense. what does it mean if it's not connected? Or, sorry, disconnected. A graph is disconnected if it's not connected. I know that's a simple definition, but in other words, it's in two pieces. So let me give you an example of a disconnected graph. Let me think. I'm going to draw this out. So here's one piece. And then here's another piece. All right, so this is one graph, but it is disconnected. And what this represents, what I'm going to say this represents, is some cities. These are, here's where we are, Baton Rouge. This is New Orleans. And this is New York. Okay, so I suppose, let me be careful here. Since I said that the vertices are typically a single letter, I could relabel these as like A, B, C. But if I'm going to give these names, this is New Orleans, Baton Rouge, and New York. And this is, let's see, I'm trying to think of my geography over in Europe. I don't have a great sense of geography in Europe, but I believe, we'll just go with this. We got Germany, we'll call that Munich, and then we'll call this Paris, France. I could be wrong, that could be flipped, but you get the point. You got the big ocean in the middle, so these are potential roads that connect New Orleans to New York to Baton Rouge. This is some road system that will connect from Paris to Munich. And then, of course, we couldn't connect the two graphs because there's an ocean. We could, but it'd be very costly. Okay. So this is, think about maybe road system. I could still get to Paris from New Orleans. I could take a flight, but these are road systems is why they're not connected. All right. And we're almost done with all our definitions and stuff. So it's almost over. A bridge is an edge in a graph so that if it is removed, the graph now becomes disconnected. So let me give you an example of a bridge situation, okay? So here's a simple graph. Maybe it's not as simple as you want, but say A, B, C. I'm gonna do a little curve because we can do curves, that's allowed. Call that D, make that a loop. E and okay. This is a little confusing. This almost looks like a single line right here, like, but that's not. It's two different things. Okay, this is different. This is different than that. Okay, so there are more than one bridge. There is more than one bridge. Okay. Notice if I remove CD, it becomes disconnected. So notice if I remove CD or DC, the graph becomes disconnected. All right, there are two other bridges. So the complete set of bridges, the bridges are CD, I mentioned that. DE is a bridge because it takes, it separates the rest of the graph from EF. So bridges are DE. I wasn't wrong. It actually, EF is a bridge, and I realize that's tricky because you're like, well, if I take it away, I mean, you got just this point by itself. But F is still part of the graph, and even though it's a point by itself, that will make it disconnected. Notice BC is not a bridge. If I remove BC, I can still get from C to B. And AC is not a bridge because I can remove AC and I can get from C to A. Likewise here. Okay, so those are my three bridges. And then my last definition and our last example is equivalent graphs. So two graphs are equivalent if they have the same vertices and the same edges. I'm going to give you another example. Let's see, V, X, W. Y, Z. Okay. I am going to do this. The homework will do this, by the way. You're going to write the vertices in a straight line. It looks so weird. And it makes me think a little harder, but they might do this. Z, V, W, X, Y. And I'm going to connect these things the same way as this. All right? So let's start with Z. Z is only connected to Y. Okay? I'm going to get to that in a second. But notice X and Y are connected. So I could do this. X connects to Y. Oh, I guess I should put some vertices, right? So there are my vertices by each letter. So X is only connected to Y. Now, X is connected to W and it's connected to V. Well, that's easy. W. But to get to V, well, I can't go through it, so I kind of have to do this. Or I could have gone underneath. V is also connected to W, so I could go back here. So it looks like that little semicircle. But Z is only connected to Y. I can't go through here because Z is not connected to V. I could go down below, or I could just do a little thing like this. So those are two equivalent graphs. I have multiple ways I could draw the same graph, but it only matters the way they are connected. Okay? So that does it for 4.1. This is probably a long video, but we had to get all the terminology and definitions and basic concepts out of the way.